Hi everyone, welcome to the webinar entitled Artificial Intelligence in the Clinical Laboratory, Implementation, Bioethics and Legislation. That is part of the IFCC 2024 live series. As an overview, I will say that in the clinical laboratory, artificial intelligence is used to evaluate test results, analyze risk profiles, diagnose, and perform financial analysis, among other things. Artificial intelligence could help reduce costs, improve access, and improve the quality of care. Its implementation requires education about the technology and research to generate clinical evidence. The widespread use of artificial intelligence has started to raise concerns. There are global discussions around security protocols that should be created to make systems more accurate, interpretable, transparent, robust, reliable, and loyal. In the field of health, it is important to ensure that bioethical principles are complied with. Legislation is an important mechanism to reinforce ethical conduct in all aspects of laboratory medicine. The regulatory framework for artificial intelligence must be designed to guarantee the safety and effectiveness of the product throughout its entire life cycle. The law must safeguard and protect data privacy. The use of artificial intelligence must be declared. Legislation must recognize the issue of artificial intelligence vulnerability to cyber threats. Finally, transforming artificial intelligence and big data into effective products, services, and processes is an expensive and risky undertaking that needs a legal structure that guarantees and provides security for the investment. Today, we have three learning objectives: to understand how artificial intelligence could be implemented in laboratory medicine, to be aware of the necessity to respect bioethical principles when implementing artificial intelligence in laboratory medicine, and to have a general knowledge of the different aspects to take into consideration in the development of laws that govern artificial intelligence. I'm honored because today we have three great speakers. The first of them is Professor Dr. Christopher McCadden. Dr. McCadden is a clinical biochemist at the Ottawa Hospital in Ontario, Canada. He is professor and vice chair of the Department of Pathology and Laboratory Medicine at the University of Ottawa. He serves as the Deputy Chief Medical Scientific Officer and Medical Director of Informatics and Information Technology for the Eastern Ontario Regional Laboratory Association. He serves as board secretary for the Association for Diagnostics and Laboratory Medicine. Dr. McCadden's academic interests include automated chemistry, data analytics and machine learning, quality improvement, plasma cell dyscrasias, and audit and feedback for laboratory stewardship. The title of his presentation is Healthcare Revolution: The Emerging Role of AI in Laboratory Medicine. Dr. McCadden, it's all yours.
Thank you. Thank you, Julian, for the kind introduction. And good morning, good afternoon, good evening, wherever you may be watching this. I appreciate you tuning in today, and thank you for the invitation to speak. So I have no relevant disclosures for this presentation, and by the end of it, you should be able to categorize different AI models, describe different AI applications in laboratory medicine, and explain some of the challenges of AI implementation in laboratory medicine. So really, I'm trying to set the stage for the other speakers in terms of some of the challenges around legal, ethical, and regulatory frameworks. So we are surrounded by AI, whether we know it or appreciate it or not. It's involved in finance, as you mentioned, whether this is from whether you get a loan or not, or detecting fraud, or whether it's doing your investing in the so-called robo-investing. It's involved in manufacturing, transportation, navigation, agriculture. There's automated tractors, when to spray pesticides, when to water, retail applications, energy, education, human resources for screening resumes or targeting particular skill sets that you might have. Environmental monitoring, trying to predict disasters or recover from them. In security, I had to use two-factor authentication several times today, which uses biometrics in order to log into my computer. But if you're tuning into this, that means there's a whole bunch of cybersecurity things that are working in the background to keep this network going. It's involved in entertainment for the books we read, the things we listen to, the things we watch. There's these recommender systems there. It's involved in law and legal services, space exploration, you name it. So this image is to try and convey all the various things it can do. Now, they say it's better to show than it is to say. And so I want you to consider this example. This is AI generated entirely. This dog does not exist. This building does not exist. The sky doesn't exist. So I want you to consider this is in one industry. So this would be in the film industry. Consider the production effort that it would take to produce this video. It's a short video versus the disruption that it might involve. And so consider in your industry and in really every industry the potential disruption that this might have and the change and the impact this can have. And it's only 9 seconds, but it's pretty remarkable what's the realm of the possible. This isn't publicly available yet, but this is something coming. It's called Sora, so entirely AI generated. But of course, AI, we're interested here in medicine. We'll talk about laboratory medicine in particular. There's tons of applications. There tends to be a lag in terms of the implementation in medicine because of the risk trade-off profile, as opposed to, if that dog doesn't look real, the risk of that is quite low. Whereas if we implement in medicine, the risks are much higher. So there are examples of use in cardiology for reading ECGs, in clinical trial design, dermatology, epidemiology, nephrology, EEGs in neurology, lots of examples in radiology of interpreting images, drug development, of course, pathology, telemedicine, so many, many applications. So what exactly is AI? I'll try and provide a framework here so you can compartmentalize some of these things. So this is one definition of AI, and I had AI actually generate me 20 of these, and I didn't love any of them, so I kind of modified this. But one way of looking at this is that AI is really enabling machines to solve problems, to make decisions using algorithms. And so if you consider AI is an algorithm. It might be something as simple as an if-then statement, or maybe something as complicated as a deep learning or a neural network. And this image here is trying to convey the potential complexity of those. So here are some AI methods. This looks like a big list, but I think it's helpful to compartmentalize these things. When you start seeing methods, you can kind of categorize them and bin them into different applications. So one method, for example, is in cognitive computing. So this is trying to make simulate artificial brains. And so there's applications here for understanding how human brains work, but also trying to get computers to think like humans. In the context of self-driving cars, consider computer vision. The car needs to see the road. Is that a pedestrian? Is that a sign? Is that a curb? In terms of robotics, it needs to be able to control the car to go in the right direction. The bottom here, there's expert systems. So imagine you have an expert in terms of categorizing a particular type of disease. If they have a series of an algorithm, a series of statements, you can have a non-expert perform like that expert if they follow that algorithm. But most of the development that we see in our field is in machine learning. And so really three major bins here. There's supervised learning, where you're trying to classify something, training it based on known cases and unknown cases. And then there's unsupervised learning, where you don't really know who, for example, does or doesn't have a disease, but you look for clustering and associations together to make predictions. There's also reinforcement learning, where you have a state, an action, and a reward, and this feedback loop. So in terms of classification, you've probably heard of logistic regression. You may have done logistic regression. There's decision trees. For example, if creatinine is X, you go this way, and if it's Y, you go that way in a decision tree. Random forest is a whole series of decision trees that work together to classify something. The ones with stars here, I'm going to show examples in lab medicine now. In terms of deep learning, convolutional neural networks are very common for image classification. I'll show examples of that. There's recurrent neural networks. These are ones which are good for time series or sequential events. So you might see these things with EEG classification. You might have heard of transformers or generative pre-trained transformers, or GPT. These have got a lot of press recently, and that video I showed you earlier is coming from a company that uses that a lot. There's unsupervised learning, where you cluster things together. I'll show examples of that in lab medicine. There's also reinforcement learning. We're trying to use this now to improve drug dosing for people with getting transplants. But there's also cross-pollination. These are not rigidly separated. For example, you can use reinforcement learning to try and improve these large language models, for example. And so all of these things may work together, and it's common to use multiple together. So what does it look like in terms of developing AI technology? You start off with formulating a problem. It's like any research, what exactly problem you're trying to solve. You collect data. Again, you need data to answer questions. The data prep and the development, validation, and interpretation, these are somewhat unique to some of the machine learning applications in the sense that you might need a lot more data. You don't need tens or hundreds of rows for machine learning. You tend to need thousands or millions. Algorithms perform much better with more data. And you tend to need to split off into training and test sets. Algorithms are going to cheat. If you give them all the data in the test set, they're going to try and use that to classify. So there's important separations that need to be done there. Developing and validating, again, someone might use multiple algorithms to try and solve a problem, and you figure out which one's the best, or you can use them together. And then there's this concept of interpretability and explainability. If an algorithm classifies something really well, you want to know that it's using the right data to do that. A classic example is a cancer data set. If all the patients, for example, that have cancer come from one hospital, while the ones without cancer come from another, if the algorithm is telling you which hospital it comes from, it's not giving you useful information. So you want to understand why it's using the classifier that it is in order to make an explanation. I'm going to focus later on implementation. There's really a gap here that we need to discuss. So what does it look like in laboratory medicine? These are a combination of things that I've seen in the literature or are applications in other fields that you might see in lab medicine. I won't go through every point, but there's a lot of opportunities here. In operations, it might be automated liquid handlers, quality assurance, predictive maintenance, making sure your instrument is always up, predicting when it's going to go down before it goes down. Process optimization, balancing workload between automation lines. We have very complicated staffing rules and scheduling and a shortage of staff, so there's opportunities there. It's amenable. Financial analysis, predicting which patient volume might be going up, which complexity might be going up, reviewing contracts, LIS mapping. In academics, both teaching and research applications, whether that's generate teaching resources, there's fantastic opportunities to use this to teach yourself, asking it to create a course for you or adaptive learning. There's great examples of this in the field where it meets you where you are and feeds you material based on your skill set. You can use it for experimental design, idea generation, writing, communication, tons of opportunities in academics. I'll show examples in laboratory medicine of using it for result interpretation and image analysis. If you think about it, depending on your definition of AI, in all our instruments, there's calibration curves. These are algorithms effectively. So perhaps we're already using them to a great extent. There's novel test examples, personalized reference intervals, prognostic opportunities, reflex testing, decision support, lab stewardship, many opportunities. So I'll go through some specific examples here in lab medicine, such as automated urine microscopy. What you'll actually find is most of the real world applications of this that exist are commercial. So these are things that you purchase from a vendor, and there are several that do automated urine microscopy. I chose to show this kind of generic image of a robot to not give anyone preferential treatment, but they're used for urine microscopy. There's also examples in computer-aided immunofluorescence microscopy, for example, for classifying ANA patterns and peripheral blood smear review. There's examples in quality assurance. For those of you looking at this, there's a QR code which will take you to PubMed for these papers, so you don't have to copy these references down. This example from Nick Spies and colleagues looking at identifying IV contamination. So for example, whether it's contaminated with water or normal saline or lactate or dextrose. And he's got some nice examples here of the ability to perform better with algorithms than humans can. And this is an example of non-supervised classification. There's also examples with tube mislabeling, auto verification, quality review, and mass spec data. So there's these great examples in the literature, really from around the world, showing sort of a lot of pre-analytical sort of algorithms that perform better than humans. It's used for result interpretation. This is an example of using deep learning for classifying immunofixation. So this is, those who read these things, it's an IgG lambda, you can see. And so this algorithm performs actually really well. Not only that, it tells you what data it's using. So this is just a heat map showing you what it's using to make that classification. You can see it really highlights the IgG lambda, which is exactly what you would expect. If you saw it using some data over here, like a label, you'd be concerned, but this shows you it's using the correct data. In fact, if you look closely, there's kind of an artifact here, and it's choosing not to use that bit, so it's actually pretty neat how it's working. There's also examples for mass spec analysis, molecular diagnostics, calling variants, next-gen sequencing, flow cytometry, you name it. The last set of examples is in kidney disease. So this is a paper that my research group published late last year, and this uses random forest classifiers to try and predict which patients with chronic kidney disease are going to progress to needing dialysis. Now, patients that have planned dialysis tend to do better than those with unplanned, and so that was the rationale for solving this problem. And so with our algorithm, we're able to predict sooner than we otherwise could using a random forest algorithm. There's also examples of infectious disease testing. Lots of these came out of COVID, drug metabolism, and so on. Now, I've painted a pretty rosy picture of the realm of the possible for AI, but there are some challenges. These include data. Do you have the right data? Is it biased just based on the population or the availability of data? Can you get enough to generate these algorithms? Those of you who have ever done chart review to generate high quality data know that that's going to be preventative if you need millions of rows. There's issues of privacy and security. I'm going to talk about implementation performance momentarily, but there's also considerations around unintended consequences. What happens if you automate your workforce? Are you going to lose jobs? Are you going to lose skills? Perhaps we're already on that road in terms of auto verification, but it's a consideration. We're now going to have a whole new class of errors and considerations because the way algorithms might fail might be very different than the way your instrumentation or your analysis fail. And the other speakers, of course, are going to talk about the regulatory, ethical, and legal frameworks. So what we find really is there's this huge implementation gap. So you have a whole pile of high quality research papers in our journals, but then the real world applications, again, are rare. There's this huge gap there. What we find is most of the applications are commercial, and that might be what we expect for the foreseeable future. And the reason for that is there's significant barriers to actually implementing these. So this looks complicated, but I'll walk you through it. In the AI pipeline development slide, I showed you this before. You're collecting data, you're developing and validating algorithms, explaining, interpreting them. But there's this other whole set of activities that are involved. And really, if you consider this, what you're doing to implement AI is you're developing this algorithm, which is a whole thing unto itself. And then you have this really software operational pipeline that you need into consideration. What does the live environment look like? If someone's developed this on their laptop, can you use the same algorithm? Maybe you have to have a different algorithm. You have to compress it, or you have to use different data. And so really, how does it perform in the real world? What are the risks to this thing for patients and organizationally? How are you going to evaluate those? How are you going to mitigate those risks? What are the security considerations? Can you audit this? For example, if you have a problem with a particular prediction, can you trace it all the way back to the original raw data in the exact environment in which it was generated? In terms of production and deployment, there's this concept of continuous integration and development, which is an old concept from the software world, but it might be something we're not familiar with necessarily. That's a whole skill set in terms of code development, sharing code, making sure all the ingredients work before it gets pushed into production. Can this thing work at a speed that you need when you have multiple clinicians using it? Or imagine you have multiple algorithms. Can all these things work together in concert to actually do what you expect it to do? So you need to put in these monitoring feedback systems. If something goes wrong, let's say you've changed your method. So you have new instrumentation, you're giving it new data. How fast are you going to be able to detect whether that algorithm is working properly? And what does that look like? And so when you think about it, there's actually a whole layer of people that we might not have thought about before. So all of you who've tuned in are arguably subject matter experts in laboratory medicine. You probably worked with IT operations to implement a new lab information system or interface instrument. Some of you are or know data scientists who work on these things. There's this whole other cast of characters where engineers in machine learning, data, quality assurance, developmental operations. And so there's other group of people. And at least at my hospitals, we don't really have these people readily available or even at all in some cases. And so really you're looking at this whole software development thing. But I have limited time to talk, so I'll leave you with this, again, of course, an AI generated image. But I think the horizon is bright and the opportunities are great in laboratory medicine. It's probably less dystopian than maybe in some other fields, but there's a lot of uncertainties to how this is going to look. And there's some barriers to getting to where we need to go. So I thank you for tuning in, and I'll pass it to the next speakers.
Well, thank you, Christopher, for your interesting presentation. The next presentation is going to be done by Dr. Dennis Ilham Topku. Dennis is a medical doctor with a PhD in medical biochemistry. Additionally, he has a bachelor in science in computer engineering. His areas of interest include pre-analytical systems, quality control applications, auto-verification, and multidisciplinary projects that involve the integration of medical and computer science. He actively uses R as a primary data analytics tool for developing machine learning models related to clinical laboratory applications, including explainable artificial intelligence projects. Dennis is a member of the IFCC Committee on Internet and E-Learning and also serves as the web editor. Currently, he's working at Izmir Tepesik Education and Research Hospital. The title of his presentation is Exploring the Ethical Landscape of AI-driven laboratory practices. Dennis, it's your turn.
Thank you, Julian, for this kind introduction.
Welcome.
Good morning, good afternoon, and welcome, everyone. I would like to begin with expressing my gratitude to IFCC for hosting this event. And also, it's an honor to be here with you today and discuss ethical landscape of artificial intelligence in laboratory practices. Thank you all for joining us in this important discussion. As a big fan of Asimov, it is almost impossible for me to start this presentation without mentioning 3 laws of robotics. Technically, I grew up at Asimov, and I think Asimov may have foreseen the critical importance of ethical frameworks in developing and applying intelligent systems. Other than Asimov fan, as a medical doctor with a computer engineer degree, I try to bridge the gap between healthcare and technology. My proficiency in both areas are central to my work and enabling me to oversee laboratory management and conduct academic research. I have no conflict of interest or financial disclosure related to this presentation. I hope by the end of the presentation, you will be equipped with a deeper understanding of bioethics in the AI healthcare context. We will inspect the ethical challenges that surface with AI in healthcare. At the end of the presentation, I am going to share some other references and further reading options for you. As mentioned with the previous presentation, we have witnessed a rapid advancement in general AI, and we have now different applications, including self-driving cars, chat robots, or chess, StarCraft playing systems, Google DeepMind. And it is not different in medicine too. Parallel to these developments, the field of medicine is also undergoing its own transformative journey, leveraging AI to revolutionize diagnostic, treatment planning, and patient care. And it is similar with our clinical laboratories. They are increasingly harnessing power of AI and machine learning algorithms throughout the all total testing process, as we see in the previous talk. I can present many examples, but they already discussed. So I want to emphasize that the integration of AI and ML is improving clinical laboratory workflows, leading increased efficiency, accuracy, and at the end of the day, we improve patient care. To summarize how AI ML works, I prepared this slide. It starts with a historical data, which AI system analyzes to detect patterns and relationships. And this analysis is used to build a model that encapsulates the insights gained from the data. When the new data is introduced to this model, the AI can apply the learned patterns to generate insights, making predictions or decisions based on the model's understanding. So actually, we need historical data, big data, and we need some algorithms or models to apply AI and machine learning. AI is increasingly becoming a staple in various industries, including healthcare, for several compelling reasons. Computers excel at repetitive tasks, while the exponential growth of available data and computing power has made AI algorithms very practical. AI can analyze large data sets, detect subtle patterns and correlations, and it can deliver consistent performance. Together, these factors make AI an invaluable tool for enhancing productivity. This graph shows a clear trend of increasing FDA approvals for AI/ML-enabled devices over the years. It is clear that from 1995 to the present, there has been a significant upward trend, as you can see here. The surge is particularly strong in specialties like radiology and cardiology. But this does not come without hurdles. There are various difficulties related to AI. Ethics represents one of the significant challenges. The rapid advancements in AI over the last decade have sparked intense debate about its ethical implications. As a result, various organizations worldwide have put forward ethical guidelines for AI. To understand these guidelines, we must start from the beginning. Oh, I don't think there is no need to go back so far, but to navigate the field of AI ethics, it is essential to briefly explore the ethics and bioethics. This figure will help us to understand how ethical principles are being adapted and explicitly applied within healthcare, ensuring that innovation goes hand in hand with moral responsibilities. First, I would like to share a simple definition of ethics. Ethics or ethos represents our way of life, encompassing moral principles that form basis of our value system. These principles serve as compass, guiding human conduct and decision we make. They also become a part of bioethics. Historically, unethical research practices and harmful medical experiments prompted the development of bioethics. In modern times, the author's book on principles of biomedical ethics is a classical for its definition of 4 principles of bioethics. These 4 principles are here. The first one, non-maleficence, avoiding causing harm. Beneficence, acting in ways that promote the well-being. Third one, respect for autonomy, upholding individuals' right to make their own decisions and choices without coercion or interference. And the last and finally, justice, ensuring fairness, equity, and impartiality in the distribution of resources, opportunities, and treatment among individual groups. These principles will reflect on AI ethics for healthcare. In this slide, I have listed different organizations that have proposed AI guidelines to navigate ethical challenges. These include frameworks like the European Union's High-Level Expert Group Guideline, UNESCO recommendations, WHO's guidelines, and OECD principles. Continuing with these guidelines, there are also other recommendations from different countries and organizations. Generally, almost all guidelines have similar recommendations with some exceptions. Here, the European Union's High-Level Expert Group guideline outlines the principles necessary for ethical AI. It should be lawful, it should be ethical, it should be robust. In this guideline, only 2 of them are discussed, but these principles actually turns into some key requirements. Similar with European Union's recommendations, UNESCO has also owned his ethic codes. It is its direction to the human rights, as you can guess, but it also includes transparency, justice, fairness, privacy, and so on. Again, I want to mention that these 2 guidelines is not directly specific for healthcare, but their basic foundation is same with healthcare setting too. For example, if we inspect WHO guideline, Guidance, Ethics and Governance of AI for Health guideline, we can see that there is same principles: autonomy, human well-being, transparency, responsibility, inclusiveness, sustainable AI, and etc. And also with the surge of ChatGPT and other transformer models, they also recently published a large language model guideline. Another organization which has a guideline and offers some recommendations for transfer to AI is Future AI. They also emphasize the importance of transfer to AI in health, which needs fairness, explainability, universality, traceability, and so on. If you want a general picture about this principle, this article has a great table that summarizes these recommendations and principles. When I look at all of them, I see a synergy, and I think the synergy between these proposed AI principles may demonstrate an evolving global consensus on what constitutes responsible AI for healthcare. Of course, there are some discrepancies between the guidelines, but in essence, they all have similar recommendations. And all these guidelines reflect the bioethical principles we have already seen. When it comes to clinical laboratories, there are 3 great articles you can read. They provide principles for ethical development and use of AI in pathology and laboratory medicine. And they also include similar principles like transparency, accountability, governance, and so on. Additionally, they also emphasize the importance of ethical requirements for data collection. They emphasize data collection because, as you know, laboratories are the principal data source in medicine. Additionally, these articles, this web article from the American Society for Clinical Laboratory Science also discusses the critical role of clinical laboratories in ensuring the ethical application of AI. It emphasizes how the unique position of clinical laboratory facilitates the interdisciplinary collaboration in value-based healthcare models. And I really like this. It provides TUBE's mnemonic, which underscores foundational principles for ethical AI in labs. Now I think it's time to explore this ethical principle. I am going to explore fairness and explainability in more detail because time constraints, and there is much more research related to them. There's a scene from Bosch Legacy, a very enjoyable crime drama series for those interested, where a black man is wrongfully detained due to misidentification by CCTV facial recognition technology. This narrative isn't confined to television. It reflects a profound and fundamental issue. A parallel exists using commercial prediction algorithms, apparently designed to optimize patient care in the healthcare system. Recent findings have shown a disturbing trend. A widely used healthcare algorithm exhibits significant racial bias. According to this study, Black patients are considerably sicker than white patients at identical risk scores. This disparity is rooted to algorithm prioritizing healthcare costs over actual illness indicators. The implicit assumption that financial data correlates with health needs overlooks a critical factor. Unequal access to care means less money is spent on Black patients, resulting in systemic disparities. This is not just a glitch, it is an indicator of a bias that can perpetuate inequality. If corrected, Black patients receiving proper care could nearly triple. This story is an important reminder of our ethical responsibilities in deploying AI. Like the wrongful arrest in Bosch Legacy, the consequences of biased algorithms in healthcare are real and profound. This concept leads us to fairness, which ensures that AI systems treat all individuals and groups uniformly, without biases related to race, gender, ethnicity, or other personal characteristics irrelevant to optimized outcomes. In practice, fairness is the keystone that well aligns with bioethical principles. Bias can have different zones. A well-known part is data bias. We know that for training AI, diverse and representative data is crucial. However, it is not limited to that only. Bias can also be algorithmic, clinician and patient interaction related based. An example of a clinician interaction related bias is using AI systems and refers to tendency to rely too much on AI when tasks are transferred from healthcare professional to AI. Therefore, fairness applies to each phases of AI system development, from training AI system distribution through business channels. These slides outline critical strategies for mitigating bias in healthcare AI. These include education, ensuring privacy, interdisciplinary approach, and so on. Explainable AI is one of the cornerstone among these principles, which also core principle for ethical AI. Therefore, our next topic is about explainable AI and its ethical implications in healthcare. There is a substantial concern about machine learning regarding its behavior. Often it referred to as a black box problem. The term black box refers to AI models that produce outputs without revealing their internal decision-making processes. This is where explainable AI comes into play, which provides explainability and interpretability. And these tools allows clinicians to make informed decisions and take responsibilities for the outcomes. I give here the explanation of this terminology, but these terms sometimes can also be used interchangeably. Nevertheless, let's look at black box more closely. A black box machine learning model processes data and delivers results without revealing its internal working. Therefore, we don't know the reasoning behind the decision. For example, consider a black box machine learning model that receives a dotted image of a cat and correctly labels it. While the outcome is accurate, there is no problem, but the path to the conclusion remains a mystery. Explainable AI demystifies these black box. It provides transparency by highlighting the model's reasoning, such as pointing out specific features like whiskers, fur, etc., that lead to identification of a cat. There are different explainability methods, and here I bring a simplified overview of these methods. First, these tools can be classified into transparent and black box models. As an example of an intrinsically explainable model, here in the figure illustrates an intrinsically explainable decision tree model used for differentiating COVID-19 from RSV infection in infants. The model makes its predictions transparently by branching decisions based on key blood test indicators, such as lymphocyte counts, C-reactive protein, among others, providing clinicians with a clear and logical path to diagnosis. Other than these intrinsic models, we have black box explainability methods, and these are more interesting, and there are lots of research about them. If we classify them, there can be model specific, which only works with specific type of models, or they can be model agnostic models. Model agnostics are more flexible and can be used to any type of machine learning model. Therefore, these tools are vital research subjects these days. We can also further classify these methods as global or local explanations. While global explanations give insight about the whole dataset, local explanations explain individual predictions. For example, as a model-agnostic global explanation, this slide showcases a global explanation of machine learning model predicting SARS-CoV-2 infection, using SHAP values to highlight the influence of routine blood test parameters. For example, white blood count is most important parameter for deciding if the patient has SARS-CoV-2 infection or not. Each feature's SHAP value indicates its impact on the model's predictions, providing insights in which laboratory tests are more significant for detecting the virus, thus aiding again transparent and interpretable machine learning in clinical laboratories. Final example is about local explanation, which is called breakdown plots for additive attributions. I presented here. On the left plot, the model predicts a normal patient because it has lower glucose levels, lower body mass index. In contrast, in the right side of the model predicts diabetes, but in this case, the individual case, the patient has higher glucose levels, higher BMI, and higher waist measurements. So these findings are consistent with pathophysiology of diabetes, which can support the physician's trust in the model's decision. You can ask why we are not using intrinsically explainable models, because their performance are generally limited and we can use them only for limited data types. So there are model agnostic approaches these days. There are other ethical AI concepts other than fairness and explainable AI, but because of time constraints, I cannot deep dive them, but they are also fundamental to AI ethics are given. While each of these principles is a pillar that supports the ethical deployment and operation of AI in any field, including healthcare. Responsibility and accountability, open autonomy, robustness is very important cornerstone for ethical AI. But navigating the landscape of ethical AI is not without its challenges. Here I have highlighted two articles that delve into complexities of fairness and explainability in AI. However, these represent just the tip of iceberg in a sea of academic research dedicated to these issues. As you can see here, there is much more to explore. The rich debate, ongoing discoveries in this field offer a fertile ground for future research. Lastly, I will try to answer one final question. What can we do as a laboratory specialist? As a laboratory specialist, we must equip ourselves with knowledge to ensure these advancements benefit our practice ethically and fairly. For those among us not directly developing AI models, it is about becoming familiar with fundamental concepts of ethical AI. Understand what a model is, what fairness in algorithmic entails, and why bias must be addressed. This knowledge empowers us to ask questions, advocate for ethical AI use in our labs. For developers, the task is more technical, but equally grounded in ethics. Leverage the robust Python and R libraries are available, tools designed to help us build, evaluate, and refine models with fairness in mind. As a conclusion, AI has become an integral part of our reality, particularly in healthcare, where its potential is as vast as the challenges it possesses. It is imperative that we commit to understanding AI's capabilities and rigorously address its ethical implications in our practice. Thank you for listening. If you need further reading, I shared this QR code, and you can reach different articles for specific laboratory or healthcare references are presented there. Thank you.
Thank you, Dennis, for your outstanding presentation. And now is the turn for Dr. Daniel Gervais. Daniel Gervais is the Milton R. Underwood Chair in Law, Director of the Vanderbilt Intellectual Property Program, and co-director of the LLM program at Vanderbilt Law School. He focuses on international intellectual property law and the law of artificial intelligence. Prior to his academic career, he spent 10 years researching and addressing policy issues on behalf of the World Trade Organization, the World Trade Intellectual Property Organization, the International Confederation of Societies of Authors and Composers, and the Copyright Clearance Center. His research was published in Science, Major Law Reviews, and in books published by Oxford University Press and Cambridge University Press. The title of his presentation is The Complex Interfaces Between Law, Ethics, and Code, and the Use of AI in Medicine. Daniel, it's your turn.
Thank you, Julian. I'm very glad to be able to join you today. I've simplified a little bit the title of the slide, as you can see, or the presentation. Like the previous speakers, I have no relevant disclosures to make. So, there we go. Today I will be discussing a number of interrelated issues. My main point, however, is to situate the interface between law and medical research to identify what I call pressure points. The use of AI presents a number of unprecedented challenges to policymakers, courts, and legal scholars, and we've already heard from previous speakers that have mentioned a number of them. The challenge stems in part from the fact that the rules that govern human behavior, including ethical rules, are based not only on law on the books, but also on certain human understandings, or what we might call values, that human actors tend to internalize. AI machines, in contrast, can mimic and in many cases even outperform humans in high cognitive functions, but they do not have inherent values. Moreover, teaching human law to AI machines is, as it turns out, extremely complex. Law is often both fuzzy and contextual. So, a simple example that I think everyone will understand is many legal systems have a notion of, quote, reasonable person, unquote. You can imagine how that is an interesting a standard to code. Uh, in medicine, AI promises, and we've heard this also from previous speakers, promises to accelerate many areas of research. However, delegating part of the research enterprise to AI means finding ways to ensure that machines operate according to human rules and standards that they cannot understand in the way that humans do. In addition, while some applications may be very valuable, they can also be used for negative purposes. For example, AI's ability to process vast amounts of data can lead to useful correlations for medical researchers between, say, genetic mutations or specific biomarkers and diseases, but the same technology can be used to deny health and life insurance. Lawmakers and regulators are considering several issues that will affect the use of AI in medical research. First, how will the use of AI machines reflect the values of human research from anything from bedside manners to in clinical trials to the prioritization of research areas? These two examples illustrate the breadth of the issue. So the first question is, what should be regulated? Second, do we need to write into legal code what doctors and researchers do? For example, the ethical rules that the previous speaker identified governing interaction with human subjects. Third, if so, how would we translate this legal code into machine code? In fact, we can't. Machines can learn the law, but only up to a point, as some recent experiments with AI compliance agents have shown. The idea is to have an AI that has learned an area of law that will then check on the work of one or more other AIs. We also know that machines work according to, obviously, to computer code, not legal code. And there are three important points to make here. First, as I said before, law is a human invention. No law can stop a hurricane or even stop a dog from barking. The law can impose hurricane preparedness obligations. It can also impose a fine on the dog's owner. But when we say, for example, that an animal has rights against, say, cruel treatment, what we really mean is that humans cannot treat the dog with cruelty. If a mountain lion were to kill the dog, no one can sue the lion. Second, we know that law is based on another human invention, language. Only humans can speak or write in a way that allows us to create and enforce legal obligations. Third, there are legal entities such as corporations that can sue in court, enter into contracts, etc., but their actions are really taken by the humans who operate them. So, in regulating the use of AI, the target of regulation cannot be the AI itself. It must be the humans who program, train, or use the machine. These are likely to be different sets of rules for each category. For example, one rule that would apply only to programmers, not to users, would be the mandatory inclusion of a kill switch to stop the operation of a malfunctioning AI. There will also be secondary liability rules for those who own AIs used in medical research, even if they are not the ones, the actual users engaged in medical research. And this will most likely create an entirely new area of liability insurance. The difference is that between the previous examples and an AI is that an AI, unlike, say, a corporation, has autonomy and agency. Unlike a young child or an animal, the AI can think or act in a way that mimics human higher cognitive functions. But in the legal system, the AI is not a person. It remains a thing, a legal object, not a subject. That means that we need clear rules for humans, including possible bans on certain uses of AI, such as the life insurance example I mentioned earlier. But we also need transparency, as was mentioned by the previous speaker, explainability, and possibly FDA type pre-approval for specific types of AI. But the FDA and similar agencies in other countries have traditionally been in the business of regulating drugs and devices, not algorithms. They have experts on staff who understand drugs and devices. Testing algorithms and data sets for potential bias, for example, is not in their wheelhouse. Now, they need experts in testing algorithms, but then they will face the issue of trade secrets. AI companies keep their algorithms even closer to the vest than their clinical data sometimes. And in the US, they tend to win when they challenge government requests to disclose their algorithms. If we want to avoid biased or otherwise unethical outcomes, such as the one discussed by the previous speaker, we probably need to retool these governmental agencies. Another way in which the impact of the law will be felt is by creating incentives, but also potentially blocking a lot of medical research. So let me explain this point. I think it's quite important. As the law stands now, a machine cannot be an inventor. But saying that is not really saying that much. And so I would like to make 3 points. First, you'd have to define as a matter of law who the inventor is if you think you have an invention. In the area of potential AI outputs, as you know better than I do, AI is now routinely used to speed up and reduce the costs of pharmaceutical and other types of research, especially by doing in silico research. Let's say that you feed a machine all the literature on a particular disease, or for that matter, all the medical journals ever published in any language, because that is also possible. You ask the machine to look for hidden patterns. The machine's output could take the form of, say, new molecules with the right properties to attack the biological targets of interest, predictions of drug efficacy, and assistance with drug design. The AI could identify the optimal chemical structures to reduce toxicity and meet metabolic needs, both of which can be costly and data-intensive processes. In all these cases, there is no invention because there is no human inventor. But it is possible that the output of the machine will enable researchers to reduce a particular drug to practice. This is likely to be a patentable invention. In other words, what is really important to understand is the crucial difference here in the definition of what an invention is between acceleration and replacement of human inventors. Second, one of the criteria for obtaining a patent is that, and this is worldwide, is that an invention must be non-obvious, or what in many countries is also called, must be the result of an inventive step. To the extent that large language models can produce new molecules with accurate predictions of efficacy and toxicity, wouldn't those results be obvious? If so, the prize will go to those who obtain regulatory approval to market the new drugs. This comes with its own form of protection, independent from a patent, this is called data exclusivity. Thirdly, let's look at what could happen if efforts to change the law, such as what, for example, is happening in Brazil, are successful. The idea here is to grant exclusive rights to machine outputs that look like they're of a patentable nature, but that do not have a human inventor. A machine could theoretically produce thousands of new compounds accompanied by some prediction of efficacy and toxicities, as I mentioned before. This might be sufficient to obtain these new rights. Since patent law does not normally require actual clinical trials, these new rights probably would not. But let's take this thought experiment a step further. Let's say the machine could run its own clinical trials. And as in a paper I published in Science last October shows, an AI could, in fact, legally run its own medical research company. And I know this sounds a bit like science fiction, but without any human oversight. Again, this is not a matter of technological possibility, but legal possibility. It probably will become a matter of technical possibility in a few years. Google has published a paper explaining that one of its AI can both identify new inventions and manage the entire patent application process. This form of automated research may well produce many positive results in medical research, but granting patents or similar rights to thousands of new molecules could also lead to massive trolling, lawsuits against medical laboratories, and so on. The solution here seems to be pretty simple. For the time being, let's just stick with human invention, remembering what I said earlier about the difference between acceleration and replacement. Autonomous, inventive machine outputs would not be prevented in any way, but they would not acquire a right to exclude everyone else from using those outputs. Let us remember also that patents are a form of incentive, and quite honestly, I do not see much evidence of massive underinvestment in AI at this point. As much as AI is likely to produce new results that we would not otherwise have, or at least accelerate those developments, it might also cut off others, and this was mentioned by the first speaker. Researchers will rely on AI tools and do less of what cannot be done without them. The same thing is happening with ChatGPT for text. Researchers, including my own students, almost all use large language models to prepare memos and papers. And as a result, those papers look more or less the same. They lose what I call personality. In medical research, what might happen is changes qualitative and quantitative in the outputs of laboratories. So quantitative, obviously, because the AI can produce more, but qualitative because the researchers will tend to rely on what the machine can help with more readily. This is, by the way, this is happening in so many other fields, music with AI suggesting melodies and chord progressions that are more likely to be commercially viable. That industry is concerned about the fact that what people sometimes call new sounds or new artists will not emerge. So this isn't just an issue for medical research. This is where I fear the law will have to step in, but it is difficult to monitor negatives, to monitor things that do not happen, but that would otherwise have. Moreover, there's very little the law can do to prevent dependence on the new AI tools. My concern here is that once we've handed over key cognitive functions to the machine, we may not be able to get them back. So in order to leave as much time as possible for discussion, just a few takeaways from this quick talk. So we need clear rules, but again, the legal rules cannot apply to the machines. They need to apply to humans, and particularly to programmers and operators of AI. We will need, and this is quite urgent, I think, to rethink the roles of regulatory agencies like the FDA in the age of algorithms, because AI is not a drug, but I don't think it is the same as a device. It really belongs in a category of its own. We'll need to find a balance between innovation and control in the use of AI in research. And I think it's important to find ways to monitor changes in research patterns and behavior. And this may not be a matter for regulators, but I think it is important to inform the work that regulators do to assist researchers in developing and commercializing their research. So with that, I will turn it back to our moderator. Here's some 3 publications that that might be of interest, including, if you interested, a book of science fiction, of near-term science fiction that I used to teach the law of AI to my students, and it has a lot of medical research in it. So I thought I would mention it. So with that, thank you very much, and I look forward to the questions and discussion.
Thank you, Daniel, for your very, very interesting presentation. And now I'm going to read some questions. The first one is machine learning dependent on the quality and quantity of data? This question could be answered by Christopher or Dennis, I think.
Going back on camera here. Yeah, thanks for the question. And so as I understood it, in case I didn't hear you correctly, they're asking whether the quality of the algorithms generated depend on the volume and the quality of the data. Is that correct? Yeah, so the answer to that is yes and yes. Typically, algorithms that have more data tend to do better, but better quality data is better. So if you had higher quality data that really gives you the key variable to make a prediction, that's going to be better than millions of rows of sort of noisy data. Like knowing someone's telephone number, you could have a gazillion rows of that, but that's not really going to tell you much about their health. Whereas if you had, for example, troponin results and you're interested in their cardiac outcomes, that's going to be much more useful. So it really is two of those. The quality of the data is probably more important than the volume, but more good data is, of course, better.
Okay, thank you. The second question is, could artificial intelligence help reduce the need for doctors to practice defensive medicine? Would doctors actually consider artificial intelligence?
I can make a comment about that. The replacement is a general issue asking for us always, but I think AI is a tool, and doctors are going to use tools like other tools like ACG device or other some complicated, for example, maybe tomography device like that. At the end of the day, this technology will help us to make better decisions. Maybe in unforeseen future they replace us, but I don't think so. It is a very near soon event.
Okay, thank you, Dennis. I have another question for Christopher. Do you think, as laboratory medicine professionals, do we have to engage in develop artificial intelligence tools, or it would be better to be good users of commercial products?
Yeah, that's a great question. I've thought about that one and talked to colleagues about that one as well. There's just two ways to look at it. There's the more you know, the more you know. If you understand how they're developing or developing their own, you can identify issues with them. However, I think it's unreasonable for everyone to develop the skill set to develop algorithms, such that I think being intelligent users and consumers of it is going to be important. What I would advise everyone is to be a subject matter expert, which is different than developing the algorithm. So anyone who's going to use laboratory data to develop an algorithm, they should involve you in that, because you know more about that data than they do. For example, something as simple as a lot shift, a new calibration, a new instrumentation, when you're producing fundamentally different data and they assume it's all the same to train their algorithm. So I would inject yourselves as subject matter experts into the field rather than, I think it's not reasonable to all become experts in those aspects. I mean, the stuff I showed at the end in terms of the software development, that's an expertise I don't have. And so being collaborative is probably the best possible thing you can do. And then looking at some of the ways, the ethical ways and the regulatory ways and the best ways to validate that technology that comes out commercially.
Thank you. Here I have another question from the audience. Do you think doctors will trust the diagnostic by artificial intelligence?
Can I chime in on this one? There's a kind of an example in law that might be useful. So when you're accused of a crime in many legal systems, the judge will decide whether you will be in jail while you wait for trial, and then after trial, of course, if you're found guilty, we'll send you to jail for a certain amount of time. And in the U.S. and many other countries now, there's AI that will suggest an answer to the judge. So they have a tablet in front of them, and the studies show that judges trust these numbers to an extraordinarily high extent, a very large extent. And unfortunately, the studies that we have show that the system is actually pretty poorly designed, and but the fact that it comes from an AI and it shows up on a screen, it gives it some sort of I almost want to use the word magical, quality. And I think doctors need to be trained very carefully, as Christopher was saying, to understand very well what the machine can and cannot do, and that whatever it says is really only a guide. And I think in law and medicine, the people who regulate lawyers and doctors will not tell lawyers and doctors, you're off the hook if you make a mistake because you just blindly followed an AI. You you need to understand what the machine can and cannot do, and I fully agree with the other speakers were saying about that.
Okay.
I want to add something to this question. The trusts, I think, come with explainability too. I mentioned black box problem. If we do not know the reasoning, it becomes difficult to trust the system. So this research area is very hot topic. There are lots of article citations about that, and it should be evolved. More explainability models should be evolved, and then we can start to trust these systems.
Okay, Daniel, you have said that legal rules cannot be applied to artificial intelligence products. Then responsibility remains on the professionals. I think that is the point.
Well, some legal rules, I would, for example, tax rules can be fed into an AI quite easily, but what really governs medical professionals, especially in as they're caring for patients, is a whole set of rules, some of which are written, some of which are not, some of which are written in very general language, rules of ethics that are written in language, human language that is meant to talk to other humans. And when you try to translate that into computer code, it becomes extraordinarily difficult. So there is ongoing work on what's known as compliance agents. So these are basically AIs that are trained to supervise the work of other AIs. This is just beginning, and whether it will actually work to understand notions like, reasonableness, for example, fairness, it hasn't been demonstrated. We're not there yet. So, and as I said before, I think the law will clearly put the liability on the shoulders of the medical professional, even if you're using an AI. And the fact that you use an AI will not be a defense saying, well, the machine said X, so I did X, and that will not work. It might work in a lab if it doesn't have consequences, but if it is a patient, there's a human subject involved, I think this would be extraordinarily difficult.
Okay, great answer. What is your recommendation about using AI in laboratory information systems for interpreting results of patients, and put some comments for the physicians?
I guess I can jump in on that one as well. Again, I think it's all about evaluating what the benefits are and what the risks are. So the idea that it can perform interpretations, I think it's inevitable, and there are probably some really good use cases for that. But you're going to want to know that it's performing well. And I think one unanswered question is what do you put in the report? Do you say it's positive, it's negative? Do you give a percentage? Do you give a probability? How do people interpret those? How do you put in comments about mitigation in terms of what the risks of that are? That's really hard to convey. We're at this point happy that they read our reports at all because of the volume of data we give them. So I think it's going to be a challenge to convey the complexity of that information, and really needs to be outside of that laboratory report before you start resulting things.
Okay, thank you. From the legal and ethical point of view, the traceability in the utilization of artificial intelligence is the most important issue. Well, I really don't understand this question. Well, here's another one. What's the biggest challenges in integrating artificial intelligence tools into existing laboratory workflows? How can we overcome them?
Yeah, I'm happy to take a first crack at that one too, because I kind of discussed it. This is a challenge I face. So we've got this nice algorithm. We have a nice peer-reviewed paper and an algorithm that works really well, and it's really difficult. So what you're going to have to do is work with other people at your institution. For example, is the electronic medical record you use or the lab information system you use, does it have the ability to integrate algorithms? If it does not, how does that pipeline look? What software are you using? And you really need support from your organization in order to do this. So there needs to be a collective will in order to implement these things. You're going to talk to others who have actually done that before and see what those options are. And you're going to want to put all those safety nets that we talked about in terms of making sure that it works well. You could consider doing a small pilot, which we're doing. So let's give it to a small subset of physicians who really understand what the algorithm can and can't do and work from there. I think going big right away would be very difficult. So you probably want to start with small use cases and then work your way up to a larger capability. But it's a long conversation. I won't jeopardize all the time with it.
Yes, really. I like this question. How does the role of the laboratory professional shift in the face of artificial intelligence automation? Where is human subjects still crucial? Then the question refers to the shift in the role of lab med professional, and
maybe I can make a small comment. With using
yes,
these tools, for example, we can filter out normal or normal like patients, and so we can spare our time with more complicated cases. For example, immunofixation about M proteins. If we can filter out normal patients, we can deal with more complicated tool peaks, maybe biclonal peaks. We can deal with that. So it takes us time. Maybe we can use AI like that.
If a quick word on that, I think what Christopher said about medical laboratories having to work with engineers is when you're trained to do in vitro and in vivo research, and all of a sudden you're doing in silico research, you're actually working with computer people, right? This is a totally different protocol, and but that's where the power of AI is to a large extent, and it creates this entirely new method in a way, which requires, I guess, a different type of training.
Okay. Yeah, I agree with both of those comments. We need to train ourselves, the current generation and the next generation, in some of the skills. And I think the analogy is that we've automated a lot of things, and our roles have changed as a result of that. So our systems, just to get a result from an automation line, are now so complicated. I don't think that we have our own people even troubleshooting these things. Now we rely on the vendors, service representatives and really engineers to do those systems. So I think Daniel's comment on relying on collaborating with people who understand the complexity of those systems is what it looks like. And then agree with Denise's comment in terms of we will just deal with higher level, more complicated problems, automate the sort of boring stuff, and we deal with more complicated issues.
Okay. Here's an interesting one. With all the fast development in the field of artificial intelligence, what could be the fate of countries which are far behind from the technology? What is your opinion?
Oh, Dennis, please.
A simple comment. It can be double-edged sword. It can be help, for example, undeveloped countries. For example, education. It facilitates education without sufficient tutors, but it can also make the difference bigger between the countries. So it should be managed very carefully.
Yes.
Yeah, I share that perspective as well. So there's two paths. It's either they're left in the dust and don't have that technology, or it could hugely advance them. Like picture not putting down all that infrastructure for telephone lines and then jumping to cell phones. If you don't have the skill set to interpret these complex, mass spectra things, if you can get something that can give you the data, it might actually boost them in terms of their ability to do quality assurance, quality control, and do complicated testing that they otherwise might not have the capability of doing if they can get there.
Well, here it says that in a recent study, 16% of the study group that use artificial intelligence cause harm to patients. Does anybody know if any other studies found artificial intelligence harm caused by artificial intelligence? 60% is too high, I think.
Yeah, I'd be interested in the context of what was being used there and those details. I'm not aware of another study. I guess the other comparator is humans cause a lot of harm in terms of medical errors too. So I'd be interested to contrast the two of them in that context.
I would add a kind of a tangential comment, but I think it's relevant. So we have a lot of data on self-driving vehicles, and they kill people, they hurt people. The question is the standard for these vehicles to hurt 0 person before they're allowed? And if that's the standard, we'll never get them. So there's a lot of discussion among regulators as to whether self-driving vehicles should be 10 times better than human drivers, 5 times better, 100 times. And I think the same will happen in medical research. AI will make mistakes, but the data we have, at least in terms of self-driving vehicles, suggests that people are not willing to accept the same level of risk with AI than with humans. They're expecting the benefit to be a lower risk, and the question is how low. And from my point of view is, do you regulate this, or you just wait, for example, for litigation, especially in the US, or how? I don't have a good answer to that, but what the data clearly shows is people expect AI to perform better than humans.
Okay, Daniel, I have a question, a personal question. What happened with the law? Because the development of artificial intelligence is so fast, and the law requires maybe more time to be enacted. What mechanism do you propose to accompany as fast as the development in medicine, for example? Is it possible to use artificial intelligence to make laws, or what is your point of view?
Well, I've been part of some experiments where people work with large language models to try to make law or figure out the rules, and let's just say it hasn't been super successful. But I would partly disagree with the premise that the law is always behind. You always hear this. So it's partly true. In the case of the regulatory agencies, there's no question that the law that governs these agencies, say like the FDA, needs to be adapted. Some people are saying it shouldn't be the FDA, it should be some other agency that does only AI, for example. There's all these debates. But overall, say I mentioned patent law also in my presentation. This is already adapted to AI. Who did the adaptation? Courts. This not just in the U.S. In Europe as well, and other jurisdictions, you have court decisions that interpret existing law as it applies to AI. Same with copyright, for example. So those laws don't need to change. And then you have the AI Act in Europe, where there are rules, and then there are agencies in each country of the European Union that will apply more specific rules. In the US, there's already an executive order from the president asking all federal agencies, well, most of them, to adapt to AI, to figure out a way to adapt to AI. So I don't think we're that far behind in terms of law. Where we have a problem is that these machines that are performing high cognitive functions, sometimes outperforming humans, have a real problem, if I can put it that way, understanding the rules by which we operate, because many of these rules are either vague or actually not technically legal rules. They're rules of behavior almost to a certain extent that sometimes cross into illegal, but not always. And explaining that to machines, that's the challenge, I think, that we face more than developing new legal rules.
Okay, thank you. And well, I have a final question for Dennis about black boxes explainability. Do you think maybe clinical trials would be a way to validate those black boxes?
Actually, there's some informative articles about explainability tools. They can be seen as false up from a Nature article. And because of this, they recommend very rigorous validation. For example, external validation using different settings. So you can be sure about your algorithm works correctly with different settings, with different populations. Then you may not need to have an explanation. This is a one side of wheel. You can go that way too. But other articles also mentions that explainability is important. You must go with that. But when I read the principles related to ethics, the clinical trials are also recommended way to apply machine learning in healthcare.
Okay, thank you. Well, and now we are going to end this session. Thank you for attending to this webinar, and thank you, Professor McCudden, Dr. Topko, and Dr. Jay Rice for your interesting presentation that provides such valuable information on the topic we discussed. And of course, thanks to Dr. Farestai for coordinating this webinar and to the IFCC for offering this tool for the e-learning. Please remember that if there are unanswered questions, they will be replied by email to those who post the question. The certificate of participation will be provided at the end of this webinar after a few questions. At the end of the question, please click to Show My Scores at the end of the page and get your certificate. And last, the on-demand content of this webinar will be available in short, and you will be informed via email. There will be soon after other IFCC free webinars, and they will be announced via IFCC communication channels, email, websites, and IFCC social media. Thank you and goodbye. Thank you.